Presentation is now for, thank you. It is Adam Kochanski from the San Jose State University Laboratory, and the title of the presentation is Leveraging Coupled Fire Atmosphere Modeling for Local Scale Smoke Simulations.
Okay, thank you for the introduction, and I would like to thank Bati and organizers for inviting me for this meeting. That's great to be finally, all together, not just via Zoom. So I'm super happy to be here, and I would like to talk with you a little bit about what we have been doing over the past couple of years in terms of using coupled fire atmosphere models for smoke simulations. So let's get started. We mentioned before during this session a little bit about the health effects, and of course that's a big motivation for us, and that's one of the reasons why we care about smoke. So of course, inflammations, asthma attacks, damage to lungs, potential risk of heart attacks, and risk of cancer. Those are all health effects associated with smoke. So that's the motivation, and that's why we try to be able to simulate how the smoke disperses, what are the concentrations, basically to be able to warn people what's going to happen. And of course, if you think about what happens on long time scales, is that we have on one hand this climate signal and change in global warming, kind of leading to increased fire activity, and then of course as a consequence of that we have more smoke, people will get hospitalized, there is going to be a risk associated with that and cost. And of course, if we think about the trends in both the temperatures, that's this red line, and with the fire activity, this area burned, that's black one. I mean, of course, we only can expect that going into the future we'll have even more fires. We'll have more fires, and of course we will also have more smoke, so that's going to be even more important. Now, if we think about modeling of smoke, at least at like atmospheric scales, there is quite a few processes that we have to consider in order to be able to simulate what actually is happening. So the first really important one, of course, is that we have to consider what is the amount of heat that actually is being released by the fire, and what are the emissions. So that's what kind of happens at the very surface. But there is another important element, which is that actually this fire itself, and we kind of touched on that, it modifies local weather as well. I mean, once you start releasing a lot of heat into the atmosphere, you will have this buoyant plume, you will have completely different circulation close to the fire just because of the heat generated by the fire itself. So that's kind of the second element that at some moment we have to consider. Of course, once we have this buoyant plume and then the heat release into the atmosphere, we'll have this convective plume being kind of transporting the emissions up. We'll have entrainment into this column. But then it's not the end of the story, because inside the column itself we'll have all those particles. We may have deposition of those particles to the ground. We will also have the cloud itself, this smoke column that will obstruct solar radiation. So we will have some smoke shading effects. Here below this anvil of smoke, of course, we will have less solar radiation than outside. So that's another really important aspect that we can consider. And of course, within the smoke column itself, there will be some chemistry going on. And after even the chemistry going on here, we may have some long-range transport and dispersion in the atmosphere. So that's a very complex problem. And of course, you can look at it from different angles depending on what you are really interested in. Smaller scales, larger scales, and what you try to attack. In this particular presentation, I will be showing 3 different approaches, how you can kind of try to leverage coupled fire atmosphere models, like similar to meso-NH for fire, and kind of link that to the air quality problem and to the problem of looking at the dispersion of smoke. So here is just an example of a simulation done with Warface fire, which is very similar to meso-NH. So basically, the whole idea is how to use the information that we can get from a model that actually resolves fire progression and the plume rise, and how to kind of inform air quality models, and how to build the whole system that will be able to compute at the same time progression of the fire, plume rise, dispersion, and all the consequences of that. So before we go into that, let me just go back a little bit and talk a little bit about how it has been done so far in the context of typical air quality models, the models that we would use to issue a warning that, for example, air quality is gonna be bad the next day. So the typical approach would be that we would start from looking at the fire area, and that would be based on the satellite detections. We would maybe use some information about the fuel moisture to be able to compute what is the fuel consumption, what is the rate of consumption. Then we would use some emission factors that would relate the mass of burnt fuel to the emissions. We would use some parameterization of the plume rise, and then we would use some model that would deal with the dispersion and maybe also with the chemistry. So there is a couple of really important consequences of this classical approach. So the very first one is that if we follow this path, if we based our forecast for the next day just based on the observations from the satellite from the previous day, well, we lose this coupling between the weather and the actual fire behavior, because the next day the weather may be different and the activity of the fire will be different as well. If we just look at the satellite, those observations from the previous day, that may not be the best assumption. Another one, very important, is that if we here just look at this fire area and the growth of the fire, on one hand, of course, if we have bigger fire, we will have more emissions. So if there is some explosive fire growth, we won't get that just looking back at what satellite detected the previous day. But on top of that, there is also another aspect that this fire may change its shape. It will behave differently one day versus the other. So assuming that everything stays the same is not actually that great of an assumption. So basically, we try here to do something about all those assumptions. And basically, instead of using this typical distribution of emissions that is assumed to be the same from day to day and just driven by the observed fire growth over the previous day, we try to actually forecast that going into the future. So how would we do that? We would do that in a basically sense of coupling two or even more different models. So we would basically have some weather component, and that's, for example, meso-NH. We here are talking about weather research and forecasting model, which is very similar. But basically, we couple that with a separate fire spread model, and in meso-NH, that would be the Balbi fire spread model. We are using the Rodermel model. But basically, idea, of course, here is that we use the actual weather conditions to drive the fire propagation, to provide information into the weather model. We use additional information from the weather model for the fuel moisture model to get also information about what is the fuel moisture. We integrate everything within the fire spread model, and based on the simulated progression of the fire itself, we compute emissions, and then we feed those emissions into this weather model, and the weather model actually does the job of resolving the plume rise and dispersion. So basically, at the end of the day, we would have meteorological output, just like from a regular weather forecasting model. We would have fire output in the context of what is the fire area, fire intensity, and things like that. And of course, on top of that, we will also get the smoke output, and that's what we'll focus on today. So here's the very first test case that I would like to share with you. That's the Paul Creek fire from 2018 in Utah. And what I'm showing here is the actual simulation that should start playing. So here are two domains. That's this dark contour, that's the actual fire, and then you see how it's growing. And this color field, that's the actual PM2.5 resolved by the model itself. And those are the wind fields that we simulated at that moment. And here is the small picture that we see that we resolved in the context of the actual progression of the fire. But it's not everything, because of course, in order to do that, we use nested domains going from coarser resolution to finer resolution. And we can see here like a bigger picture being a consequence of this particular fire. So of course, it's not that the impact of this fire is just local. We resolve it at local scale, but actually everything is kind of nested within a bigger system, so you can also see what is the longer range transport of the smoke and what is happening here. One important element that I would like you to just focus on just for a second is that you see how variable the dispersion of this smoke is. When we look again at this simulation, you will see that there are periods where this smoke completely misses Salt Lake, which is here, but from time to time you see this tongue of smoke going straight into the valley, impacting all the population living here in this area. So here is a map of our domain, and that's what we are talking about. And for this particular test case, we were very lucky because we had a network of observations that we could use to validate our model, how well we can simulate the concentrations near the ground. So we used those relatively cheap purple air sensors that people may not trust too much. We use also air quality sensors, which are those indicated by those blue triangles. And on top of that, we also used measurements taken from this train that is kind of crossing across the valley. So this was really a good test case, because it's not that you just have one point, even if those stations are not perfect, but at least you can get like extent of smoke and basically use this information to understand what's going on. So here's an animation showing one of those episodes where you see that the smoke is entering the valley. And it's very interesting because, as you see, it's like not all the time. I mean, it just happens in certain hours, and it's associated with the flow here and down the valley, up valley winds, and basically having a model that resolves the atmospheric flow at high resolution allows you also to capture some of those circulations, which are then very important in the context of dispersion of smoke. So here is the actual city, and you saw this tongue of smoke going into the city itself. Here's another example from the same simulation. So this white contour, that's the fire, and here you see the simulated field. So all those colors, those are the concentrations, and all the dots, they show the actual measurements. So you see that actually we grasp pretty well those gradients in the valley, and the extent of the smoke itself actually is captured pretty well in this particular case. So that's a very important thing, because we don't want just to give an information, hey, tomorrow is going to be smoky, because it's really hard to make decisions based on that. If you can tell, hey, there is going to be smoky and unhealthy air will be from 11 till 12 or from 11 to 1 p.m., then you can react and you can stay at home during that time, not go out. So there is a really big value in being able to precisely identify where and when those high smoke episodes occur. Of course, there is a lot of things going on here, and I'm not going to go into details, but I just wanted to highlight this one slide showing also the same tongue here of smoke going into the valley. And here, this line that you see changing colors, that's the observations from this train. And the reason why I want to point it out is that, look, even if you look at this scale, which is just within the valley itself, there is really wide range of values. It's not that all the valley will be under, let's say, unhealthy conditions. You will have, in some case, maybe 80 micrograms per cubic meter, or 90, or even more than that, but just a couple of kilometers away, you may have pretty clean air. So, of course, if you want to warn people, I mean, you don't want to say, hey, yeah, everybody should just stay at home, because it's not exactly the case. I mean, having information about the actual extent of the smoke is very important here. So now let's just look at the actual values. In this particular case, we are looking at one of the stations, and that's the time series of the simulated PM2.5 concentration during this Paul Creek fire event. And you see, again, here in this data, that we really capture very well this spike in the PM2.5 concentrations associated with this surge of smoke into the valley. So that would be our 24-hour forecast, and it's really well done. However, of course, later on, I mean, it's not that easy to tell what's going to happen, let's say, over the next day. And here we do a pretty good job in terms of capturing the magnitude, but in terms of the timing, we have some shifts. So, of course, it's not a perfect solution for every single problem related to smoke. And of course, it's understandable because that's going to be related also to our ability to tell what the fire is going to do over the next day and the following day. And of course, that's difficult. And here's just a snapshot of the plume top height simulated by the model, and at the same time, just a satellite picture just showing the location. And remember, that's actually the location of the smoke when it doesn't really impact the communities. And we don't have the satellite images at the moment when the smoke gets into the valley, but fortunately we had those measurements from the ground stations that I just showed you a minute before. So then you can start asking questions, okay, so if we saw those errors, I mean, how can we attribute those errors? What the actual problem is? And one of the really important aspects is how well, again, we simulate the actual fire progression. If you look here on this map in the left corner, you see here the observed fire perimeter, and that's this yellow line. And you see the forecasted fire perimeter or extent of the fire, and that's this red field. And you see that in the context of the Paul Creek fire, those two parts of the fire, it actually worked pretty well. However, for this Bald Mountain fire, which actually started before the Paul Creek fire kind of merged together, I mean, here the model really overestimated the rate of spread. So, no surprise, if you look at the forecast here, I mean, you see that those spikes in the PM2.5 concentrations are higher than what actually was observed. And that's something that kind of links again together those two words, like smoke and what we do in terms of the air quality and what we do in terms of the fire forecasting. If we can improve the forecast of the fire progression itself, then we can leverage this information and use it in air quality model as well. So the take-home message number one is that those high-resolution coupled fire atmosphere simulations, they are useful in the context of understanding those smoke episodes, and also they have some skills in terms of estimating future PM2.5 concentrations. But there are some limitations. One is that in this case, we just treat smoke as a passive tracer. We don't really, at that moment, look at any chemistry involved in the interaction between smoke and anthropogenic emissions. So we just leave it aside. That's number one. And of course, again, linkage to the fire behavior itself. I mean, the fire behavior and being able to simulate that accurately is absolutely critical here. So, the next step, what we will be discussing, is a little bit different approach. So first, I will be talking about how we could couple this fire atmosphere model with an external model, but with the chemistry, to have on top of just the regular tracer being advected, also some kind of chemical transformations within the plume itself. And then we'll go to another approach where we try to integrate everything together, have a fire model linked two-way with the weather model and with the chemical transport model. So here's an example based on the air-packed air quality system, which is used in US for Pacific Northwest. And again, the standard approach would be that you would have meteorological data going into the system. Then what you would do, you would just use observations from the satellites and this assumption that, okay, we observed what happened and we'll use the same information for the next day. Based on this previous day growth of the fire, you would estimate your emissions for the next day in this preprocessor. Then you would feed it into the chemical transport model, and then this chemical transport model would provide you a map of future, let's say, PM2.5 concentration, ozone, and what have you. So that would be the typical way of doing business. So what I want to show you today is a little bit different approach to the same problem, where instead of using those observations from the satellite, we will be trying to plug in here the coupled fire atmosphere model and actually simulate progression of the fire, simulate the plume rise, because here, if you use just the satellite data, you have to parameterize plume. Here we will be resolving the plume, and we will be trying to put everything together to get to see if we can get better representation of the future air quality, low air quality episodes. So here is the second test case that I will be talking about. That's Cougar Creek fire from the Washington. So you see here those set of domains. We start from really coarse resolution, and we go into higher and higher resolution till we can resolve conditions near the fire itself. Here is just a list of stations that we use to compare our results with this classical approach and with the approach when we used a coupled fire atmosphere model to provide information about the plume rise and rate of spread. And here is the actual simulation. So you see here is the Cougar Creek fire just starting from the point source ignition, and it starts developing, it grows. Depending on the time of the day, we'll have different moisture conditions, different atmospheric stability, so this plume will behave differently. And here we will be just taking information from this model, we'll feed it into the CMAC model in terms of the plume top height, in terms of the growth of the fire, and we'll be using this information to create an air quality forecast. So here, of course, the important element will be how well we simulate the actual fire growth. And I'm showing this particular test case to highlight one thing. This growth that we have here simulated using the coupled fire atmosphere model, that's the red line. Those observations from the satellite pixels and from infrared perimeters, that's the black line. And you see that they are not perfect. We started at like relatively good agreement, but then the model kind of is a little bit too slow, then it is too fast, and finally they match. But it's not that it's like perfect solution. So let's see if that even works, if we can get anything out of that, because at the end of the day, it's not going to be just the fire growth itself, but there will be another really important aspect, which will be the plume top height. And that's the forecasted or simulated plume top height from this particular fire. You see how variable it is at two domains. So that's this innermost domain at 444 meters. That's going to be a 4-kilometer outer domain. You see some of the long transport. And let's see, are they even different, those plume top height estimates? Well, it comes out that they are quite different. So if you use just this feed of data from the satellite and you try to parameterize the plume top height, you will end up with something like 2.8 kilometers of, that's going to be your injection height. If you resolve the actual fire progression and you start to resolve the actual convection and the plume development, well, you will have completely different results. Here we are talking about 2 kilometers. So which one is true? Well, it comes out that we had a miser overpass during this particular fire, and you see that the observed mean plume top height here was around 2 kilometers. So we had from our simulations 2,200 meters, so we were, let's say, within 200 meters off, but it was still much better than this assumption of using just the satellite observations from the previous day and driving everything with that, because that ended up giving you a mean plume top height around 2.7, 2.8 kilometers. So does it make any difference if you change just the plume top height and you replace those observations from the satellite with the forecasted fire growth, even though it's not perfect? Well, it comes out that actually it improves pretty much every single aspect of those simulations. So the blue table here basically shows mean error, root mean square error, and all other factors. If you look across this table, I'm not going to be talking about everything, but basically no matter which aspect of this table you look at, which column, at every single one you will get an improvement. So getting a really good representation of the plume dynamics and then the vertical extent of the smoke column, it proves to be really, really important. So even if you don't have a perfect fire growth, it still may give you pretty good results. So that's a very important message, because it means that, well, this plume top height is absolutely critical in this particular case, because it's going to determine how the smoke is going to disperse. So even if you don't do the perfect job in terms of simulating the fire growth, but you improve significantly the plume evolution and representation of this process in the system, you can have improvement in the context of better representation of smoke concentrations near the ground. So that brings us to the third method. So let's say that we want to, instead of having just those models linked together, in a sense that we have information from the coupled fire atmosphere model being used as an input into the air quality models, but imagine that in this case there is no feedback, yes? I mean, so the air quality model will know, okay, that was the plume top height, that was the amount of emissions, but then you can ask a question, well, yes, but we'll have some smoke in the atmosphere. We may have interaction between the smoke and, let's say, radiation. We may have some warming or cooling, and if we just feed the information from one model into the other without this feedback going back from the fire model to the atmospheric model, we will miss something. So here we extended this system that you looked at before, and it's very similar, but there is just one extra component, which is that instead of using just purely weather model to simulate the actual progression of the smoke, I mean, let's say plume rise and then dispersion, instead of treating that as a passive tracer, just something that flies around but doesn't chemically react in the atmosphere, what we do instead, we just use information from our emission module, and we feed that into the WRF-Chem, which is the chemical transport model, which is two-way coupled with the weather model. Okay, so that's the only difference with respect to the previous case. So that's the test case that we analyzed. We looked at 2018 California fires, and the reason for that is that there was a lot of fires, and you see that they created like a mosaic of smoke, which came out to be very persistent. And then those smoke lines that you see, those are actually canyons in complex terrain, where the smoke was very stagnant and it couldn't be really mixed out over a couple of days. So we wanted to investigate, is that something related to the impact of smoke itself on local weather conditions? Is it why it was so persistent, or something else was going on? So that kind of ties to just this idea that if you have smoke in the atmosphere, it will interact with the solar radiation. So you may have some scattering, you may have some absorptions at higher levels, but if you have some aerosols in the atmosphere, well, they will reflect, they will absorb some of the radiation, so at the end of the day, the solar radiation reaching the ground will be lower. So potentially, as a consequence of that, you will also have reduced incoming solar radiation near the ground, and also reduced temperatures, and you will have more warming at higher elevations. So potentially it may induce this heating at higher elevations, and it can change stability, and if it changes stability, it may also change plume dynamics, and it may change everything. What we want here to do is basically to recognize and to identify if this radiative impact of smoke is really important, especially if we are talking about short timescales and the regional approach to this problem, because we are here not talking about like climatic impacts of the smoke in the layer. It's more like we are talking about local impacts, let's say over the area of couple hundred kilometers at most. And another important aspect here is if how do fires and this wildfire smoke actually impact local temperatures? Is anything meteorologically different if we have smoke in the atmosphere versus a case where we don't have any smoke? And of course, another really important question, if we build a model like that, can it actually resolve some of those impacts of the smoke on local weather conditions? So here is the configuration that we used. We will be looking here at a little bit larger scale than what we talked before. So you see that's like a region of like 80 kilometers. And we actually simulate multiple fires here. So those are like 1, 2, 3, 4, 5 different fires. And we use WRF as fire coupled with the chemical transport model, which has aerosol scheme called go-kart, and this aerosol scheme is linked to the radiative scheme in the model itself. So those aerosols in the atmosphere, they will interact with incoming solar radiation, and we will be able, by looking at the outputs from the model and turning this effect on or off, we will be able to identify what's happening. So in this particular case, we don't really freely simulate those fires. Instead, because that's for historical period from 2015, we actually reconstructed progression of all those fires by just creating fire arrival time. that Roberta mentioned in her presentation. Very similar approach, just a different scale. So we just replay progression of those fires, and all those fires grow over a certain period of time. In this particular case, we were talking here about, if I remember correctly, about 10 days, and we just simulate the emissions, we simulate the plume rise, we simulate dispersion and those radiative effects. So here you see those are those active fires. You see here the smoke that kind of gets trapped and it's really persistent. Before it gets ventilated, you have like another surge of smoke going into the region. So those are basically those elements that we are focused on here. Those regions and those periods where this smoke really stays for a long period of time and creates really unhealthy conditions with high PM2.5 concentrations. So that's the domain, again, but we are looking at the terrain. So you see here all those sharp gradients in the elevation. Those are the canyons. And if you remember the plot that I showed you before, it really resembles those lines of smoke. So actually, that's what we are looking at. We are looking at canyons pretty much filled with smoke. And we'll be looking at observations from 2 different stations, and one will be really deep in one of those canyons, and another one will be at higher elevation a little bit, and we'll be comparing results for those 2 stations. So here is just another look at simulated PM2.5 concentrations from those fires. So that's basically the baseline simulation that we have. And you compare this simulation when we have smoke which is radiatively active to a simulation where we assume that smoke doesn't do anything. So basically, instead of having this coupling through the aerosol scheme, we will be comparing the results to a pure simulation with the fire, but completely ignoring the impact of smoke on radiative heat budget. So of course, before we go into that, we have to verify if we even get the plume top height correctly. So that's a similar plot to the one that I showed before. We are looking here at the Miser observations from the satellite, and you see pretty good agreement. It's even better than in the previous case. So we are really spot on, 2,200 meters. That's the Miser observed plume top height. Simulated one is at 2,200 meters, roughly at the same level. So we are confident that at least in the terms of the vertical extent, we do a good job. So now let's look at what happens at the ground, at those 2 stations that were shown on the map. So here I'm looking just at the solar radiation, and you see that between 19th and 20th, that black line, that's the observed incoming solar radiation, and you see really big decrease in incoming solar radiation, and that's the indication of the impact of the smoke itself. And here those 2 color lines, the red one is just the simulation where we don't have any coupling with the chemistry and we ignore the radiative impact of smoke. And the orange one, that's the one when we actually resolve the fact that the smoke is going to absorb some of the radiation and there will be less solar radiation near the ground. So you see, that's the difference between those 2 simulations, that what can be attributed to the smoke itself. And that's a pretty substantial difference. So here we are talking about, let's say, 300 watts per meter square. And that's for the station deep in the canyon when we have really thick layer of smoke above it. And here is the second station, this Trinity Camp, which is much higher. And here you see that this reduction in the incoming solar radiation is much smaller. And it kind of makes sense. It has smaller effect because the layer of the smoke that is absorbing solar radiation is smaller as well. But another important thing is that it's not just the fact that we have reduction in the incoming solar radiation, but of course that also translates into changes in the surface temperature. And in this particular case, if you look here, this difference between this orange line and the red line, and in this case it's going to be around 3 degrees of Celsius. This 3 degrees of Celsius difference is going to be just the impact of the smoke itself. So that's how much cooler the surface is going to be because of the thick layer of smoke within the canyon. And of course, if you look at the station which is at higher elevation, the thinner layer of smoke, this reduction is going to be smaller than in this particular case. So that's another explanation what is happening and why. Now, you may then ask, okay, so we have the smoke, but probably it's going to have different impact at different levels and at different times, and that's exactly true. So the most intense impact of the smoke itself will be in the afternoon hours. So we will be talking here about up to 3 p.m. You see a lot of cooling near the surface, and that's what those blue colors indicate. We'll be talking about up to, let's say, 3 degrees of Celsius. And at the same time, you will have some warming effect aloft associated with the absorption of the solar radiation by black carbon. So, but it's not the end of the story, because, okay, well, we know that we have smoke, and the smoke reduces temperature near the ground, absorbs solar radiation, but how at the end of the day does that make smoke actually stay for a longer period of time in those canyons? Well, so it comes out that there is a positive feedback mechanism going on, and it works in a sense that we start from a situation when we have more smoke, and more smoke will basically reduce incoming solar radiation, so it will reduce temperature near the surface, and if we have cooler surface temperature and we have more stable atmosphere, we'll have also less vertical mixing. It will be more difficult to mix out the smoke, and as a consequence of that, we'll also have reduction in the PBL height, and as a consequence of that, the concentration of smoke is going to be even higher. So if you look here at this map, that's the PM2.5 concentration map. And here you have reduction in the solar radiation. We are talking about up to a couple hundreds of watts per meter square. That in turn is going to change local surface temperatures. And here we are talking about significant cooling. That actually translates also into reduced vertical mixing and reduced winds. You will have weaker winds, so you will have less potential to mix out and to ventilate the smoke. You will have reduced also PBL height up to a couple hundreds of meters because of the smoke itself, and that it will result in increase in the PM2.5 concentrations in the ground. So this map here, it basically shows how much more PM2.5 you have in the ground because of the presence of the smoke itself and the impact of smoke on local atmospheric conditions and this whole feedback mechanism. But it's not everything, because if you think about this positive feedback mechanism, how do you know that it is positive and that's actually a feedback? Well, if you imagine that you have your emissions and you look at the concentrations, and here we are talking about the average values within the domain, normally you would expect that if you increase your emissions, let's say by a factor of 2, you will also observe 2 times higher concentrations, twice as much emissions, 2 times more PM2.5 near the ground. But what happens is that would be kind of idealized scenario if you didn't have any positive feedback. But the actual thing that is happening here is that because of this feedback mechanism that I just discussed, it comes out that if you start increasing the emissions, and you can run multiple simulations to do that, well, it comes out that if you increase your emissions by a factor of 2, the actual concentrations near the ground is not going to just double, they will be 3.5 times higher. So that kind of highlights the reason why looking at those interactions between the smoke and the atmosphere itself may be important in the context of air quality simulations, because if we are talking about, let's say, 3.5 versus 2 times in the emissions, that may be a difference between, well, just not that bad air quality versus absolutely unhealthy air quality and stay at home. So basically, that brings me to the third take-home message from those studies that we performed, that the simulations that we run for those 2015 California fires indicate that the smoke actually can have really significant impact on local weather conditions. This cooling, changes in the wind speed near the surface, a reduction in the PBL height, that's going to be important. Also, not only that, but accounting for those wildland fires using coupled fire atmosphere model may really help forecasting impacts of wildfires on air quality. So that's really important aspect as well. And that brings me just to my last slide. Those are those 3 different aspects that I discussed today. We started from something very simple. We just use coupled fire atmosphere model and treat smoke as a passive tracer. We can go a little bit towards more complex system where we would have hybrid approach. We will feed information from the coupled fire atmosphere model into the external chemical transport model. That can help out as well, mostly because of the better representation of the plume top height. or you can go into this fully integrated system where you will have all the components linked together. And of course, the caveat is that if you go from this one to this one, of course, it's going to be more and more computationally intensive. It will require more time to run those simulations. So you will have to compromise a little bit and decide what actually you want to do and to what degree you can simplify the whole problem, basically to make it manageable. And that's everything. Thank you, and I'm ready for your questions.